Phillip Alvelda is the founder of Cortical. He was previously at DARPA, where he was a program manager responsible for the NESD program, and an engineer at the NASA Jet Propulsion Laboratory. Phillip is a scientist, engineer, serial entrepreneur, and educator, and we are very happy to welcome him back here today.
Thank you, Lisa. So I'm excited to be back at MIT yet again. My friends, colleagues, former classmates, and professors. I'm here to talk to you, in a little bit of a divergence from my last few presentations, on a new direction to take what we learned at DARPA, interfacing machines to the brain, and thinking about how to apply them much more broadly into making next generations of artificial intelligence. And I think in all of the previous talks we've heard today, there's a huge and growing groundswell of research, development, applications in industry. But there are some fundamental problems where the industry as a whole is stuck, relying on industry standard tools. And we stand on the brink as a society of making some profound decisions about what do we allow AI to do? How do we trust it? And here, when I talk about biological and digital trust, the topic of my presentation today, I'm not talking about digital certificates and software security. I'm talking about how could or should you, we all, society at large, trust machines? Because we're on the brink of giving more and more machines more and more control, and in fact, of decisions that have life and death consequences. Driving cars, conducting medical diagnoses, planning medical interventions, caring for the elderly, making these decisions without human intervention. And so I'm going to talk about, first of all, trust between you and other people, so we can kind of develop a little bit of common language and a framework for discussion, and then apply some of those ideas to guide us and tell you why we have chosen those areas at Cortical to focus on new technology development to build trustworthy machines. So let's start by looking at these one-year-old computers. They are incredibly capable. We talk about how can they identify patterns, how can they have object permanence, developing the fundamental cognitive abilities of someone learning to navigate in the world, to reach out and touch something that they see. And really, in a way, that's been the focus of artificial intelligence for a long time. Can we make a synthetic system that accomplishes some of these intellectual cognitive tasks? But when you think about trust, there's a really important other feature in this image that is very, very powerful. And that is that even before the age of 1 year, the computer on the right was able to look at the computer on the left and see that something was wrong and share a moment of empathy. So that is exhibiting personal, emotional state. The baby is upset, but also awareness of an emotion in another. How do we build systems that even in their earliest nascent capability have more of these types of frameworks so we can develop a framework of trust with artificial systems? How can we go from just thinking about intellectual quotient and capability to emotional intelligence for social interaction and consideration as a foundation for trust? So let's take a couple of examples where some of you who have had kids have been in this moment. And I'd like you to think of that moment, that very instant, where you were facing off with either a babysitter or a nanny, and you were having to make the decision in your first interview, should I trust this person with my child? What are the things that you consider? She looks reasonably healthy. She's not going to fall down dead while she's caring for my baby. Has she taken the CPR certification class? Does she have basic capability? Does she look and sound like she has good judgment? What does that mean? How do you determine someone that you're interviewing in just a few minutes of exposure, and your wife is waiting for you to get in the car and go to the restaurant and see the show, but you have to make that decision. Do you trust them with the baby? Can they foresee the consequences of bad things happening? Foresight is hugely important. That means there needs to be some sort of common framework of where did you go to school? Have you done well? Did you crash the car? There's a notion of having enough experience to foresee when something as bad as is going to happen. Is the baby crawling towards the socket on the wall to plug themselves in? Are they the ones that will notice that sort of thing? If they're eating a bite of food that's too large, could they choke? So foresight, very important. So the notion of experience, foreseeing the consequence of some action, and hopefully intervening in some way, or if something really bad happens, having the training and the capability to mediate and manage a bad situation as it evolves. So a whole set of things evolve into your decision of whether to trust or not. Let's take another situation. This one happened to me just a couple weeks ago. My 16-year-old daughter. You got to hand her the keys at some point without you in the car. And how many in these audience have had that experience recently of those white-knuckled rides around the parking lot where you can't quite reach the brake, but you can maybe grab the steering wheel in a pinch? But those sorts of moments, those are building the capability. But before you get to this moment of handing them the keys to the car, you have to trust their judgment. Very similar kinds of framework, not just capability, foresight. Understanding the consequences of your actions. How many of us have either friends or colleagues or people in the community where some 16-year-old new driver got excited with friends in the car and drove off the road and hit a tree? 30,000 people a year die in those kinds of situations. So trust and consequences, huge. Foresight, critical. But underlying all of this, think of these two situations that I gave you as a first example. Interviewing the babysitter, training your daughter to drive a car. Underlying all of this is the assumption that you can communicate with them and have discussions about things like ethics and responsibility and fear and damage and harm to yourself, harm to a baby, harm to general society. Okay? These are all difficult concepts upon which our notions of trust reside. So now let me turn it around a little bit and ask you a couple questions. How many of you today would trust a robot school bus driver to take your kid to school? Who would drop them off and say, yep, go? I got 3, 5, 7. Come on, this is MIT. This should be like a forward-looking area. You should be aware that the statistics of self-driving cars show that per driver mile, there is less likely to be an accident in one of these robo-buses than any normal bus. So why aren't we all raising our hand? Well, come on. I mean, it'll be friendly. It'll go up, hey, Finley, come on, get on the bus. It can use a cartoon voice. Everyone's happy. No? You're not quite there yet. Well, what about this one? This is the Da Vinci surgical robot. A remarkable machine. It advances every year. Some of you may have seen it in use. Has anyone had a procedure with a Da Vinci in this room? It's usually about 2%. We got one in the back. How'd it go? Thumbs up? Oh, you haven't? You've used it? Okay. I want to talk to you afterwards. But, you see pictures of these types of machines operating, and a couple things occur to you right away. The first is that the doctors are not necessarily attending the patients, they're attending the machines that are attending the patients. And if you kind of dig into the rate of advances in the software of the machines, there are like little macro features that are built in. Like, you have a picture of the patient, you've got the microscope looking at the patient's, area of operations, and you can kind of draw dots on the screen and say stitch, and it'll automatically do this line of perfect stitches. And so it's pretty clear that technology, wherever it is today, every quarter, every year, there's a new capability that automates more and more features of the robot surgeon. Today it's clearly an amplifier and a miniaturization and precision instrument to improve how an individual surgeon operates, but there are more and more macro features every day. At what point does it become, mostly the machine making the decisions and the surgeons just kind of supervising in case something weird and unexpected happens? So we're headed there very rapidly. So this is why I started the new company, Cortical, is to build technology frameworks where we could learn what are those things that are happening in human brains that form a foundation for ethics, abstract thought, the foresight of consequences, and develop a system that could put in silicon a more synthetic version that has those kinds of capabilities. So you could have conversations, a common language. How do you talk about abstractions? How do you talk about ethical and social issues? And so, of course, we looked for this next generation AI in thinking about how the brain has taught us all of these things that we've learned through 60 years of neuroscience and the last 15 years of DARPA investments in building artificial systems that couple to real brains. And to do that, we, of course, had to build AIs that would mate to the real intelligences, the wet intelligences, and develop common representations of data, understand what the code is, and being able to do things like control prosthetics with the signals from the motor cortex to drive an artificial limb. Or more recently, in the NESD program that I started while at DARPA a few years ago, how can you write synthetic images directly into the visual cortex to address blindness? Or the same for deafness or aphasia, the locked-in syndrome, where you can read the brain activity and then allow someone who can't control their physical musculature to be able to communicate. And on the left here, you see the work by Adam Gazzaley at UCSF, which they have taken the cortical tractography and these fantastic new headsets where you can go to his lab in San Francisco and have this thing on your head and watch the real-time flow of information through the nerves in your brain. And when we start to say, all right, well, we're starting to decompose what the real brains do and how they represent these things, our artificial systems, starting in the 80s, when kind of in the last resurgence of neural networks, you see kind of a diagram that would be typical for image recognition for digits. But that's come a long way. And so this last couple years, what you see on the right are these beautiful graphics that are done by a company called GraphCore. And these are renderings of some of the most advanced, state-of-the-art artificial neural networks to solve very critical problems. Let's zoom in on those for just 1 second. So here's 2 examples. On the left, you've got the deep voice. So this is an architectural rendering using the same kind of image processing we've used and developed to look at actual human brains and figure out what they're doing, but applied to the actual synthetic version of deep voice. So this is the speech recognition engine that's in the Google Assistant. And on the right, you see a convolutional image network called AlexNet, which is pretty much the foundational architecture for identifying faces in photographs at Facebook. So Jan LeCun's convolutional network architecture. And when you look at them this way, don't they look organic? Don't they look almost neural complexity level similar to the brain? And it's no accident. If you look at the statistics of how these new state-of-the-art systems at this level of complexity are performing, they are now at or better than human performance levels. And in terms of number of connections and density of systems, it turns out that for the tasks that they do, they're about the same level of complexity, maybe slightly higher, than some of the areas that perform those same functions. So for Alexa and Siri, the voice recognition network at the top of the motor cortex, where you're interpreting speech signals, and then, of course, the visual cortex for phone identification, for photo identification. Now, when you ask the question, well, we've got broader applications for things like ethical decisions in assigning care and planning treatment. Or in a car that's going to approach an intersection and has no recourse but has to hit something, who do you hit or not? These are more general questions that involve social context, information, money, personal state, who's in the car, a world model, a knowledge of the people that you're impacting. But we haven't built those pieces of the brain yet. Now, we know some of those pieces, and by the way, this graphic by Greg Dunn is a cross-section of an actual brain rendered in this wonderful etching. I'd encourage you to go and look at his work. But just that one cross-section shows you a level of complexity, and it's kind of like the old maps of the world, as we were starting the age of exploration. We have a couple areas that we know and we understand well enough to build systems that perform at equivalent or better performance levels, but the rest, thar be dragons. And so for us at Cortical, we are trying to fill in some more of this map. We are working on the systems to do things like develop a next generation of AI knowledge graphs that are organized much more like the human brain is organized, so that it can do more human brain-like things. We're looking at a next generation cerebellar model, which is not just a sequence memorizer, as people had thought. We'll talk about that in a moment, but it's a predictive engine for all of your cognitive processes. And then finally, we're looking, like a couple of other groups, at a synthetic hippocampus that can synthesize all of these disparate systems and generate more general solutions that require combining different modalities and different data types, and not just doing correlation like the current systems do, but actually preserving the object and the semantic information that's in each of those modalities and using that to compute the way your brain does, and coupling that with memory and so on. So those are kind of the three areas that we've really focused on in the early parts, and I'll dig into each one in turn. The first one is this notion of an anthropomorphic map of how abstract thoughts are represented in the brain. And so this is work by Jack Gallant at Cal Berkeley that we funded through DARPA, and some other folks I think also participated in that effort. And it was a beautiful series of experiments where they would put a user inside an fMRI and they would read to them. And they started correlating the high-density kind of activity information across the brain with the semantic concepts that were represented in the speech stream, and how that would, kind of stream by in time. And they developed this just fabulous map of how the different abstractions were represented across all the different brains. And so now, you'll see this in this great graphic. They can map places and feelings and actions and so on as it's represented in the real human brain at a level of complexity that we've never been able to build in any bespoke or programmed knowledge graph for an artificial network. And the kind of things that they could do was to look at, for the different types of people and personalities and personal interactions, places, actions, and feelings, different categories of how each of these areas in the brain activate and what the time course of those things are to represent all these different ideas. And they found that when they just decomposed the brain into 60 different areas, so this isn't even imagining a super high resolution, super fine system. Just with 60 different voxels of about a centimeter cubed in volume, they're able to disambiguate about 60,000 different abstractions. Now think about that. So we have a basis set of 60 loci. And with that, we can represent 60,000 abstractions exactly like the human brain does. But, the part of what's a little bit deceptive about this kind of decomposition is that this is a snapshot of a moment in time. And it turns out that memories, what you remember, is not a single snapshot. What's embedded in you, in your experience, are sequences of snapshots, or almost real-time videos, progressions of your experience over time. Your memories are not static. And so it turns out that time course and prediction is key. Now, we learned this at DARPA when we kind of came at it backwards from an engineering perspective, where we were working on making prosthetic arms, and we had funded a fellow named David Borton, who was then at Stanford, now he's at Brown, where they have a monkey. They put some of those motion capture fiducials that they use for the movie motion capture effects, and they wired it up. On the top right, you can see the bands around the muscles that were recording the muscular activity. And they had an implant. You can see the bottom right. You can see the activity of the actual motor cortex that's sending the neural signals to control all these things. And they built these physical models to say, all right, now we can look at the entire system from the kind of driving intelligence to the muscular actuation to the actual motion of the limbs. And we can build a model. So we should be able to make a controller that if you know what you want the arm to do, we should be able to send the signals and receive it from the brain and decode it and so on. But it turns out that the first few decoders, we just use standard simple neural networks, feed-forward networks. And we program them and we train them with all the input and the correlations of all the systems. And they kind of worked, but not great. And it wasn't until we built a predictive system, I mean, we're engineers, what do? We say, well, we got a control loop, we'll do a PID loop, and now you've got a predictive prior to inform your model of what the future estimate should be, and of course, the performance gets better. And we built that kind of with the kinematics of the arm in mind, and the performance improved, but still not great. It didn't work well until we built that same predictive element into the actual patterns of neural activity in the brain that were initiating the control sequences that the system actually began to perform. And so it was a clear pointer for us that predictive elements were super, super important. But that's not the only place that prediction turns out to be important. And one of the things that we were beginning to learn more about was what the cerebellum was doing in the brain. Now, for 60 years, neuroscientists have been saying the cerebellum is coupled to muscle memory. And after experience and practice, you build in the sequence of typical patterns of controlling your muscles. And after learning and training, you can ride your bike without thinking about it. So after doing that, you can ride your bike and probably answer a phone call and talk. You can't do that while you're learning, or otherwise you fall over. But there's this fundamental learning aspect. The other aspect, it turned out, is that all of these physical tasks that interact with the real world, it turns out your neurons are really slow. Certainly compared to electronics, but they're slow even with respect to someone tossing a ball to you for you to catch, or a tiger leaping out of the bush. And it turns out that your brain doesn't actually work on the real-time sensory information that's too slow. You'd miss the ball, you couldn't hit the fastball, you couldn't jump out of the way of the tiger. Your brain actually operates about 300 to 500 milliseconds in the future on an estimate provided by your cerebellum and the rest of the cortical circuitry. And your sensory information is kind of reconciled with that future estimate to generate, what you should be doing, and how does your action meet, racket to ball and so on. The final bit that was critical was that this wiring from the cerebellum that's generating these future estimates, it doesn't just go to your motor system, it goes to all of your cognitive processes. So, for example, you can predict the next word that's going to come out of my mouth without me saying it. You can exit the building and know what you expect to see outside. You can anticipate the future based on what you saw coming into the building. If there's a giant yellow clown out there, we'd all be surprised. And then we'd pay attention. And that's another interesting bit. Not only can we make a prediction and anticipate from our experience what should happen, we can direct that attention with our will. We can say, if I turn right out of the building, this is what I should see. If I turn left, that's what I expect to see. You generally can only explore one of those at a time. But the predictive key is a fundamental piece of managing these cognitive tasks. And the one that I want to highlight in this case is emotion. So this is fabulous work by Lisa Feldman Barrett, who's at Northwestern and MGH and Harvard. She's got a series of papers and presentations talking about how emotions are not these singular parameters. They are these predictive sequences of experience that are informing our likelihood of survival. A predictive sequence. And more than individuals and how they're represented, the notion of empathy is two people that are using kind of nonverbal and verbal signals between them to synchronize their notion of what are they predicting the other person to react to, or how predicting how the other person will react to your communications. So what we're starting to do is we're starting to tease apart what are the fundamental building blocks of abstract thought representation. How can we predict? How can we build an artificial cerebellum that will allow that predictive capability for developing models of emotion? How can we take what we read from the topology and the evolution of these abstract thoughts and apply it to an artificial system of more anthropomorphic knowledge graphs that can do more anthropomorphic things? And we chose those three items. A more anthropomorphic method for embodying cognitive abstractions, emotions, harm, benefit, friend, enemy, self, other, society. A predictive system like the cerebellum to help imagine and quantify the consequences in the future of current decisions. And then a system like the hippocampus that can synthesize all of these things across broad contexts, sensory modalities, information types, to apply all of these things in more general challenges. And we chose them because at the foundation, we see those as the core components of building a digital system for value judgments and ethics. And more than that, when you think of building a system that has those capabilities for making an agent, an artificial intelligence that represents those capabilities, it's not just good for representing artificial intelligences and making them more capable, it's also good for making models of other people. So when I'm thinking about my own cognitive processes and looking at, the people in the back that are kind of nodding off or reading on their emails, I've been in that position. I can empathize. The talk's long, he's boring, when is it going to stop? He's over time. Okay, I have a model for you in my head based on my experiences, but I recognize that the model for you should be different than my model. God help you if you've got a BlackBerry. I don't have a model for that. But the point is that now we can build agents that are more anthropomorphic. We can build user models that are more anthropomorphic. And we can start to build frameworks, digital frameworks for what's acceptable behavior for myself as the agent, what's acceptable behavior for how the agent will interact with a user. And I believe I can build digital empathy by spawning thousands of sub-processes and sub-models with these same core components. And so at that point, we've got a framework for digital ethics and digital empathy that you could apply to any industrial challenge or global challenge. And we've got systems which can be much better at precise control of complex systems based on emotions. So we see these technologies as the future for next generation avatars and robotics, which can control 50 muscles in the face in much more naturalistic ways, just the same way we controlled 12 muscles in the artificial arm so that they looked realistic instead of robotic in the prosthetics. And with those sorts of technologies, we believe we will generate what we hope will be the first generation of truly trustworthy machines, because you can have real conversations about real ethical issues, real social issues, abstract ideas in human language that we understand in all of these technology areas. Thank you very much. Yes? Yeah, I think that's a fair question. So at some point, you need some physical substrate that will store the idea of what is a behavioral model. And you need something that is going to supervise and correct. And just like your baby, you don't trust your baby, you don't trust your daughter until you've trained her with the car and she's gone through the driving training and can get insurance and pay for the gas and all those things, can change the tire if it's broken. So there's definitely a supervisory component that's necessary to make these things work. So I'm not suggesting that that's a solved problem, but the point is that for the first time, we've got the artificial systems at their root that can be architected much more like the humans actually behave. So we hope to make some significant advances that way. But great point. I'd love to talk to you about it afterwards. Yes?
Maybe I've missed it, but I haven't seen an explicit reference in those 3 areas that you're targeting for your development about self-consciousness. And the question is, do you think that is actually an important dimension to develop ethical and fully formed judgment, or you think that machines can go out without being self-conscious and still behaving in the most, appropriate way?
That's a great question. I have made some profound statements about what I think self-consciousness is, but they're completely unsubstantiated. What I will retreat to is to say that I think that the notion of consciousness, you can have any of your favorite philosophers talk about what consciousness is. but actually have started to look at consciousness on a gradation of complexity. You know, what stage of consciousness have you achieved? And when I start to look at the very the rudimentary blocks of what makes something, you know, self-aware or thinking of its own survival in a conscious way, all of these can be rooted in some notion of predicting what is going to happen to yourself. So have a notion of self, a representation of self, and projecting that into the future. And so I actually think that the fundamental rudiment of consciousness is a predictive engine. And if you start to look at the simplest organisms like bacteria that can, you know, figure out how to rise in the daylight and sink during the night, you know, they have the beginnings of a sensor system and state within them that can develop a kind of a dynamical system that predicts what the environment is going to be, or that responds directly to it. As the systems get more complex, they can predict farther into the future with more input and more complexity. And so, in a sense, there's kind of a gradual buildup of consciousness. My dog has a cerebellum that's pretty sophisticated. She clearly has object permanence. Okay, that's about 6 months in a child. So I think that you can begin to have those discussions of, you know, when does the car become conscious? You've got to build some of these foundational systems, but we're definitely headed in that direction in the growth of complexity. Yes?
So most of what you're talking about is ethics within the construct or the constraint of narrow AI. How are you looking at integrating ethics for each narrow so that there's a core or general ethics substrate?
Yeah, no, that's a great point. When you look at the elements, I talk about ethics and judgment, you know, being fundamentally, you know, one of the fundamental building blocks being a predictive system. There's predictive systems all across your cortex at different scales. There's predictive systems in your eye that when an object is moving across your retina, you know, it's most likely to track in the direction of motion. And so there's fundamental predictive motions kind of in the biophysics of how the light is impinging and the thing travels and how are the things interconnected. So that all is kind of at the micro, you know, call it the narrow AI level. Okay, there are mirrors of that in the visual cortex. But what we do know is that level of prediction tops out at about somewhere between 15 and 70 milliseconds. Okay? But your brain clearly has other systems that can look much farther in the future. I can look into the future and anticipate, you know, when I land from my flight in DCA, you know, the cab line is going to be long and I have to get an Uber going home. So I can, with attention, look much, much farther into the future because I've got machinery that synthesizes from the cerebellum, not just from the visual cortex, but from all of my sensory modalities and my memory. Okay, so that's all accessible to the predictive engine. So the key, I think, to go to the general AI systems beyond the limits of the narrow constraints is to have a predictive coprocessor that has global connectivity when you're making predictions about specific things. But yeah, that's another great topic. Would love to talk to you afterwards as well. Anyway, I think we're probably nearing the end. Oh, do you have one more question here?
When do you expect general AI to have singularity on Earth?
Ooh, wow. I don't expect an instant singularity. I'm not a Kurzweil acolyte in that sense. You know, what we're seeing is a very different progression where we're understanding the brain and what it does bit by bit, system by system. And we're using kind of those microsystems that we understand and replacing those functions where there are deficits. So it's not like it's going to sneak up on us and all of a sudden, oh my God, it can turn on the nuclear bombs and off we go. I don't think that's in the cards. They have to get agency. They have to get you know, a level of physical capability that doesn't exist yet. So I think it's going to be a gradual slope that we're going to have plenty of warning about. Hey, John.
Yeah. Fantastic, brilliant work. I'm kind of obsessed with both the intrinsic and the unintended bias in machine learning, and what that immediately takes me to is, as we move into a world of thinking in silico with machine learning, we have so terribly neglected the cognitive bias associated with thinking in carbon, our brain. And so what I'm trying to imagine is the convergence of how we develop a user interaction model between human and machine, not the singularity,
Yes.
but the meshing that accommodates the fact that the average physician has like zero training in cognitive bias, and the science is really solid, and they make cognitive bias errors every single day. And now we're introducing machine bias in silico without ever having addressed the bias in carbon. So how do you see the future of meshing an awareness of those two types of bias, which are quite different, but will be soon synergistic in every decision we make?
Yeah, I love that question. I've been obsessing about this myself. So another cause for beers after the meeting. I think the potential opportunity is one of building systems that can represent these biases in more digital and quantifiable form. And so if we can better approach how the human brain organizes it and build synthetic systems where we can lay it out and measure it, then we're in a position where we can make an agent model, we can monitor the physician and make a physician model, we can monitor the patient and build patient models. And with the cloud, we can spool up however many thousands of those you want, and now we've got a digital system that we can quantify and optimize and measure. Are there biases? What are acceptable behaviors? Is there a flagging system where we can notice now using this quantified system that the physician is making a cognitive bias? Be aware, socioeconomic bias, or be aware, preferred treatment and expertise bias. Be aware, selection bias. I mean, whatever it is that you want to talk about. But the point is, we now have a framework that can capture all the complexities of those interactions across modalities and begin using it to tune, how do you optimize the whole system for success. But yeah, would love to talk to you more about how to do that.
Thank you very much.
Thanks, Lisa.